The 8085 microprocessor requires a clean regulated plus 5-volt supply to operate. This is provided on pin 40 VCC. The voltage must be stable within plus or minus 0.5 volts and have low ripple less than 50 millivolts to avoid timing errors. Pin 20 is the ground GND reference completing the return path for all currents analogous to the sea level in a topographic map. A periodic clock signal drives the internal state machine. The external crystal or resonator is connected to pins 36x2 and 37x1. For a 3 MHz crystal, the period T equals 1 over F equals 1 over 3 MHz, approximately 333 nanoseconds. The 8085 divides each clock period into 4 phases T1 to T4 for internal sequencing. The clock edge is used to latch address and data lines, generate internal control pulses, and step the program counter. Practical example: if the crystal deviates by plus or minus 50 parts per million plus or minus 150 Hz at 3 MHz, the period changes by plus or minus 0.005 nanoseconds, usually negligible for the 8085, but excessive deviation could cause setup-hold violations on the data bus, leading to bit errors. Therefore, designers often add a small ceramic capacitor approximately 30 picofarads and a resistor approximately 1 kilo ohms to dampen load variations and ensure a clean waveform. In summary, VCC supplies the necessary power, GND provides a reference return, and the crystal clock dictates the rhythmic progression of all internal operations. The 805 communicates data using an 8-bit bidirectional bus named D0 to D7. Each line carries a single binary digit 0 or 1, allowing a full byte 8 bits to be transferred in one bus cycle. The bus is multiplexed with the address bus during the first half of a machine cycle via the address latch enable signal, after which it becomes a pure data path. Signal timing is synchronized to the clock. During any T state, the data must be valid for the central 50% of the clock period, called the data valid window. For a 3 MHz clock, T equals 333 nanoseconds. This means the data must be stable for at least 166 nanoseconds centered on the rising edge. Setup time data must be stable before the clock edge is typically 20 nanoseconds, and hold time data must remain stable after the edge is about 10 nanoseconds. Example: in a memory read operation, during T2 the address is latched, AL goes low, and the processor asserts RD low. The memory places the requested byte on D0 to D7. The data remains stable throughout T3, satisfying the 166 nanoseconds window before the processor samples it on the next rising edge. Because all 8 lines transition simultaneously, the data bus behaves like a multi-lane highway where a complete vehicle, the byte, travels together, minimizing latency compared to serial transfer schemes. The 8085 can address 2 to the 16th equals 65,536 distinct memory locations, ranging from 0000H to FFFFH. This addressing capability is realized through 16 address lines, a 0 to a 15, each representing a binary weight 2 to the 0 up to 2 to the 15th. The processor places the target address on these lines during the first half of a machine cycle while AL, address latch enable, pulses high. External latch circuitry, often a 74LS373, captures the address when AL is asserted, freeing the bus for data transfer in the second half. Memory mapping determines which address ranges correspond to ROM, RAM, or input-output. For instance, a typical 8 KB ROM might occupy 0000H to 1FFFH. 16 KB RAM could be placed at 2000H to 5FFFH, and the remaining space 6000H to FFFFH allocated to peripheral registers or additional ROM. Mathematical example: to access the byte at physical address 0x37A2, the binary representation is 0011, 0111, 1010, 0010. Therefore, a 15 to a 8 equals 0011011, which is 0x37, and a 7 to a 0 equals 10100010, which is 0x2. The processor asserts these values on the bus while AL is high, An external latch stores 0x37A2 for the subsequent data read/write phase. Correct address decoding is crucial. Miswired AL or missing latches can cause address/data contention, leading to corrupted reads or writes. The 8085 uses several dedicated control pins to orchestrate bus transactions. RD read, active low. When asserted, the processor requests external memory or input-output to place data on D0 to D7. The read pulse typically spans two T states, T2 to T3. WR write, active low, indicates that the processor is placing valid data on the bus for external devices to capture. The write pulse usually occupies T2 to T3 as well. IO/M determines the nature of the address. A high level selects memory space, while low selects input-output space. This line allows the same address bus to address both memory and peripheral ports without extra decoding. A LE address latch enable pulses high during the first half of the opcode fetch T1 to latch the address onto external latches. After a LE falls, the same lines become the data bus. HOLD, an external device can pull this line low to request control of the bus. The CPU finishes the current bus cycle, then deasserts HOLD and raises HLDA. HLDA hold acknowledge goes high to acknowledge that the processor has relinquished the bus, allowing the requesting device to drive address/data lines. These pins act like traffic signals on a busy intersection. For example, during a memory write, the sequence is a LE address latch, then WR assert low, then data stable on D0 to D7, then WR released. Proper timing ensures no two devices drive the bus simultaneously, avoiding contention and potential damage. Reset: a low-level pulse minimum 74 microseconds forces the processor to clear its internal registers, set the program counter to 0000H, and enter the initial fetch cycle. This is analogous to pressing a start over button on a game console. Abbreviated interrupt request: a general-purpose edge-triggered input. When asserted, the CPU completes the current instruction, then performs an interrupt acknowledge cycle IO/M low, RD low, to fetch a vector from the external device and jumps to the address supplied by the device. RST 7.5, RST 6.5, RST 5.5 : fixed vector hardware interrupts each line when pulled low, forces the CPU to push the current program counter onto the stack and jump to a predefined address 003CH, 0034H, 002CH. Respectively, these are useful for high-priority devices because they bypass the inter-acknowledge sequence. SID serial input data and SOD serial output data provide a single-wire asynchronous serial link. Data is shifted in and out synchronously with the CPU's clock via the trap pin or a separate baud rate generator. For example, to transmit the byte 0x5, the CPU toggles SOD according to the start bit 8 data bits LSB first, and stop bit timing, each bit lasting one clock period or a multiple thereof. Interrupt handling sequence: device asserts inter. CPU finishes current instruction. CPU acknowledges with a special M1 cycle external device, places an opcode on the data bus. CPU executes the opcode, usually a call to the ISR. ISR ends with RETI, which pops the return address and resumes normal execution. This mechanism allows the CPU to respond to asynchronous events, keyboard press timer overflow, without constantly polling. The 8058's internal register file consists of 9 8-bit registers plus 2 16-bit pointers. Accumulator A is the central operand for most LU operations such as add, subtract, and OR, and so on. All arithmetic results are automatically stored here unless a different destination is specified. General-purpose registers B, C, D, E, H, and L can be accessed individually or as 3 16-bit register pairs. B, C, D, E, and HL. The HL pair is frequently used as a memory pointer. For example, move a M reads from the address stored in H. Program counter PC is a 16-bit register holding the address of the next opcode to fetch. It increments automatically after each fetch. Branch instructions load a new value. Stack pointer SP is a 16-bit register pointing to the top of the stack in RAM, used by push, pop, call, and return instructions. Flag register F contains 5 status bits: sign, 0, auxiliary carry, parity, and carry. These flags are updated by most ALU operations and guide conditional jumps, for example jump if carry, jump if 0. Data path: the ALU receives two 8-bit operands from the register file, often A and the source register or memory. Multiplexers select the appropriate sources based on the decoded opcode. The result is fed back to the destination register and simultaneously to the flag unit. A separate internal bus, sometimes called the internal data bus, carries intermediate values between the register file, ALU, and the external bus during memory cycles. Practical example: the instruction add B performs a gets A plus B. The ALU adds the contents of A and B, sets flags, for example carry if there is an overflow, and writes the sum back into A. No external memory access is required, making this a single byte minimal latency operation. Understanding the register set and data path is essential for optimizing code, as certain operations, for example using HL as a pointer, avoid additional address generation cycles. When an opcode arrives on the data bus during the opcode fetch machine cycle, the instruction decoder examines the 8-bit pattern and determines the micro operations required. It outputs a set of microcontrol signals that drive the internal multiplexers, ALU, register file, and external bus. The decoder also programs the timing generator, which produces a sequence of T-states, T1, T2, and so on for the current machine cycle. Each T-state lasts exactly one clock period, T equals 1 over F, and defines the timing of control signals. For instance, a typical MVIR data instruction involves opcode fetch 3 T-states. T1 a LE high address placed on bus PC incremented. T2 RD low data opcode appears on D0 to D7. T3 RD high as LE low. Memory write 3 T-states to fetch the immediate operand. T4 address PC placed on bus a LE high. T5 RD low immediate byte appears on D0 to D7. T6 RD high a LE low data loaded into register R. The decoder asserts IO/M based on whether the instruction addresses memory high or IO low. It also generates WR for write cycles and RD for read cycles. The timing generator ensures each control line is asserted for exactly one T-state unless the instruction specification requires a longer pulse. For example, INXRP needs 2 T-states for address increment. Design-wise, the decoder can be implemented as a ROM lookup table, 512 by n bits, where the address is the opcode and the data word encodes the sequence of control signals and the number of T-states. The timing generator is a state machine driven by the clock that steps through the pre-programmed sequence. This coordinated operation guarantees deterministic execution timing, which is critical for real-time embedded applications where cycle-accurate behavior is required. Explanation: a machine cycle is the fundamental unit of time the 8085 uses to interact with memory or input-output. Each machine cycle comprises one or more T-states, each equal to a single clock period T equals 1 over F. The total execution time of an instruction is the sum of the T-states of all its constituent machine cycles. Steps to estimate execution time. Identify the instruction's machine cycle breakdown from the instruction set manual, for example MV, IR data equals opcode fetch plus memory write. Count the T-states for each cycle, opcode fetch equals 4T, memory write equals 3T, etc. Add the T-states to obtain the total number of clock periods. Multiply by the clock period T to obtain the duration in seconds. Mathematical example: at 3 MHz, T equals 333 nanoseconds. Instruction MV I0x55 consists of opcode fetch, for T equals 4 times 333 nanoseconds equals 1.332 microseconds. Memory write fetch immediate operand, 3T equals 3 times 333 nanoseconds equals 0.999 microseconds. Total equals 7T equals 7 times 333 nanoseconds, approximately 2.331 microseconds. If the same instruction runs on a 5 MHz clock, T equals 200 nanoseconds, the total becomes 7 times 200 nanoseconds equals 1.4 microseconds. For more complex instructions such as LD, a load accumulator direct the cycle breakdown is Opcode fetch equals 4T. Memory read low address byte equals 3T. Memory read high address byte equals 3T. Memory read data byte equals 3T. Total equals 13T at 3 MHz. Execution time equals 13 times 333 nanoseconds, approximately 4.329 microseconds. Using this methodology, developers can predict the worst-case execution time of critical loops compute CPU utilization and ensure that time-sensitive tasks meet their deadlines.